Okay, so if you look at this table, we have got four functions, f1, f2, f3, and f4. So you can see the truth table. It's a long truth table, a large truth table over here. But what we are interested in is their outputs. So these are all Boolean expressions that we can derive the logic schematics of it. So if you look at f1, f2, f3, and f4, I'm just asking to you if you can spot anything with their outputs. So think about it for a second, and then I will explain what will be F1, F2, and F3, and F4. Can you spot something over here from their outputs if you look at the truth table? Okay, so if you look at F3 and F4, now F1 is just giving some outputs, F2 is just giving some outputs, but F3 and F4, they are just having the same outputs. Okay, now when we look at their expressions, let's start with F3. So F3 is equals x prime y prime z or x prime y z or x y prime. Now, when we think about this expression, I have got three inputs over there, three inputs over there, and two inputs over there. This is an AND with three inputs, AND gate with three inputs, and AND gate with three inputs. And they are all combined with an OR function with three inputs. Okay? Now, how can I draw that? I have got an AND gate with three inputs, x prime, y prime, z. Another AND gate with three inputs, which is x prime, y, z. And AND gate with two inputs, x, y prime. And they are all combined with an OR function into one single expression, which is F3. So this is the logical implementation or circuit implementation of F3. And what we have used, 2 and 3 functions. Sorry, this is N2. 1 and 2 function, and 1 or 3 functions. Okay? So this is the cost of our implementation. Now let's check F4, which is going to give us the same expression. So F4 is x, y prime or x prime, z. Now what I have got over here, AND gate with two inputs and 2, AND gate with two inputs, and of course and OR gate over there, which they combined with two inputs. Now if I implement that, AND gate with two inputs, AND gate with two inputs, sorry about the size of my gates, about my drawings, this is all I can have. F4, and this is x, y prime, this is x prime, z. Now, we have used 1, 2, and 2 functions, and 1 or 2 function. So the cost of the system, we have got 3 gates, and they are all 2 inputs gates. Okay? And if you look at this one, I have got 1, 2, 3, 4 gates in total. And some of them are 3 inputs. As you can see, we have got 2 inputs and the 3 inputs. So F3 has got more gates than F4. So as a designer, which one would you prefer to have? F3 or F4? So most of the designers, As we are thinking about the more compact and more cheap and area efficient solutions, we go for F4. So what we are going to try to do in this rest of this course, we are trying to reduce the expressions like F3 into form of F4 so that we can have more economical implementations in the case of area, in the case of cost, and in the case of power consumption, as we have got more gates over here. So these are all coming to a form in algebraic manipulation. Okay, so this is what we are going to see next, algebraic manipulation. Now with algebraic manipulation, when a Boolean expression is implemented with logic gate, each term requires a gate, each variable within the term designates an input to the gate, and literal is a single variable within a term like a prime, or x prime. Okay, so terms and variables and literals are all important. And when we consider these 4 different expressions, you can see that we can have different terms and literals in each gate. Now, we can analyze this like F1 has got 1 term, which is n term, and 3 literals, x, y, z prime. F2 has got 2 terms, or an nth, and 3 literals, x, y, and z. And F3 has got 3 terms, and, or, and also 2 inputs, and we have got 8 literals. So 1, 2, 3, 1, 2, 3, 6, and 1, 2. In total, we have got 8 literals. Now, manipulation of these Boolean expressions, we can either reduce the number of literals or maybe the number of terms. So we can have less, simpler, less area, and cheaper circuits. So that's what we are aiming in this rest of this chapter, to have efficient expressions by using algebraic manipulation. So let's see these examples. X dot x prime plus y. X prime plus y. So when we consider this as an expression, I can multiply these out. So x dot x prime or xy. Now what is x dot x prime? It's x dot x prime is always 0. 0 or xy is what we are going to get. So if you OR something with 0, you're actually going to get the original value, which is xy. So this is the first one. You can try it by yourself if you want. Then we have got x plus y and x plus y prime. Now, we can solve it in 2 ways, but I'm going to show you the long way of this. Either, so let's say x dot x, x dot y prime, and then y dot x and y dot y prime. So x dot x or x y prime or xy or y dot y prime. So x dot x is x, y dot y prime is always 0. And what we have left is xy prime or xy. Now, as x is common for all of these, I can take x out, and this is going to be 1 plus y prime plus y. So anything ORed with 1 will give us 1. So x dot 1 will give us x. And that's the answer for the second one. And the last one is x plus x prime y. If you do remember the theorem slides, what I can do is I can distribute these over. So x plus x prime and x plus y prime. So x plus x prime is going to give us 1. So 1 dot x plus y prime is going to be x plus y prime. Oh, sorry, x prime y. I wrote it other way around, I guess. So this is going to be x prime y. Let's take it over again. So 1 and then 1 dot x plus y, and then this is going to be x plus y, not y prime. So these are simple operations that we can perform, and we can take this further and we can see standard forms of or canonical forms of algebraic equations. So what are those canonical and algebraic forms of these operations? Like we have got, let's say, end function. So end operation. Now, in the AND operation, this is important. A, B, and let's say we have got F as an output. What do we know? 0, 0, 0, 1, 1, 0, 1, 1 for two variables, four possible combinations. So F is going to be 1 when both inputs are 1, and then the rest will be 0. Now, when we consider this part, we can write this as a expression, as a variable. Okay, so what do we mean by that? This is going to be, as both are 0, so we are assuming A should be valid when it is 1, then A is 0 means A prime, B is 0 means B prime. And then this one, A is 0, A prime, B is B, and this one is A and B prime, and this one, it's going to be both A and B. So then we can say that F in the AND gate is A dot B because of that. Okay? So this is how we can represent an AND function or any type of AND expressions, which is a product expressions. So each of these four AND terms are actually representing minterms, we call it, okay, or standard product, okay. So minterms, that is like an n terms that we can have for a logic function. So n variables can actually give us to the power n minterms, okay. That's what we need to know. And the same thing applies for the OR function. And OR function, we have got A, B, and F again. So 0, 0, 0, 1, 1, 0, 1, 1. And this is going to be 0, 1, 1, 1. Now with the OR function, I'll use different color. Now it's just the opposite of that. So which we call it standard sums. Now in this case, 0 becomes A and 0 becomes B. And we have got OR in between those. And then 0 becomes A, 1 becomes B prime. So it's just an opposite of n, the product terms over there. So this is going to be A prime or B. And the last one is A prime or B prime. And these are all OR terms. And we call it standard sums or we call it max terms. Okay, So this is how we are representing this as a standard forms. And we can actually summarize this in a table where we have got x, y, z, 0 to 7, 3 variables. You can show it 2 variables or 3 variables, but let's show it in 3 variables. N terms, x prime, y prime, z prime, and it goes up to x, y, z in original form. So when x is 0, we represent it as prime. When x is 1, we represent it as x. And designation is using small letter m's, m0 to m7. And the max term, which are OR terms, it's going to be opposite of that. So when it is 0, it's x. When it is 1, it's x prime, and they are all OR together, and that is designated with capital M 0 to capital M7. Now, how are we identifying the min terms and the max terms in a function? That's what we are going to see next. So if you consider this typical truth table of a function where we have got x, y, z. Now, in order to find the min terms, we look at where the function f1 is output as 1 in 3 places. Function output as 1. So those are our min terms. So if we look at this one, it's x prime, x is 0, y is 0, and z is 1. So x prime, y prime, z. Okay? So x prime, y prime, z is the first min term. Which min term is that? Min term 0, min term 1. So this is min term 1. Then I have got another one, which is x, y prime, z prime, x, y prime, z prime, and that is min term 4. 0, 1, 2, 3, 4. Min term 4. And then repeat for the last one. It's x, y, and z, and that will be min term 7. So we can say that f1 is equals x prime, y prime, z, or x, y prime, z prime, or x, y, z. Or in other words, I can say that this is equivalent to sum of the min terms. So f1 is equivalent to sum of the min terms 1, 4, and 7. 1, 4, and 7. So I can write it in this form. Okay, so this is how we are actually deriving the sum of the min terms or the product of max term, which I will show you that as well. So let's see these in the slides as well. The first one is x prime, y prime, z, which is m1, which we already got it. The second one is x, y prime, z prime, x, y prime, z prime. That's min term 4. They're all OR together. And then the last one is x, y, z. Okay, so we are actually having ORing these n terms, or actually summing these n terms to form the function, which we call it sum of products, SOP. Okay, so this is example 1. Let's see another example. F2. Now we have got 4 output as 1. So let's start with this one. This is going to be x prime, y, z. The first one. X prime, y, z. Then we have got x, y prime, z. Then x, y prime, z. This is min term 0, 1, 2, 3. This is min term 3. And this is min term 5. And then we have got x, y, z prime, min term 6, and x, y, z, which is min term 7. And when we OR them together, we have got 3, 5, 6, 7 as sum of min terms, and that will be our expression. Now, these are easy to find out. And we can easily find out the max terms as well. So how are we going to do that is the question. Now, as we already found, let's go back to F1. As we already found this, when we are applying to the ones and identifying which ones are 1, the zeros are left alone. Those are actually going to represent our max terms. So how are we going to do that? What we can do is we can write which ones will be the max terms. Okay, so let's write it as max terms. Now, if you consider it, this is 0, 0, 0, which is F1, it's going to be 0. So I can say that F1 prime, okay? So F1 is representing ones, F1 prime represent zeros. What do we have over here? Minterm 0, this is minterm 0, minterm 2, 3, 5, and 6. Minterm 0, minterm 2, minterm 3, minterm 5, and minterm 6. Okay, so those which are not included as when f is 1 is actually representing our max terms. So if you write an expression for it, f1 prime is going to be x prime, y prime, z prime, or x prime, y, z prime, or x prime, y, z, or x, y prime, z, or x, y, and z prime when you consider it. These are our minterms. Now, as this is f prime, I have to use De Morgan and take the complement of that. So that means we need to have f1 as it is, and I'll take the complement of those expressions. So this is going to be x, y prime, z prime, or x prime, y, z prime, or x prime, y, z, or x, y prime, z, or x, y, z prime. Now, if you take the De Morgan of that, that means we have to take the complement of each operation and each variable. So f1 as the max terms are going to be x prime plus y plus z prime. And x plus y prime plus z, x plus y prime plus z prime, and also x prime plus y prime plus z for the final one. And these are representing our max terms, which are m0. So let me take it from here. So this is going to be 1, 0, 1, which is m5. This is going to be 0, 1, 0, which is m2. This is going to be 0, 1, 1. As in the max terms, we are taking the opposite of those. This is going to be m3. And this one, maybe I skip 1. And this is going to be 1, 1, 0, which is m6. I think I have skipped 1. And that's going to be as x prime or y or z prime. Okay, and this is actually 1, 0, 1, which is m5. Okay, so by converting or taking the De Morgan of each, we can easily find out the max terms. So the steps are, first, identify as the min terms, but it's going to be the complement of f for zeros. Then take the De Morgan of it, and then write them as the max terms. So I can actually represent this as f1 product of max terms are 2, 3, 5, and 6. So I actually included 5 over here and there. You don't need to write it twice. I accidentally write it twice. So you can get rid of 1 and 2, 3, 5, 6 are our max terms. And you can also see this on the slides as well, which are the similar steps that we have followed. So finding out the F1 where it is zeros, taking the complement of F1 prime as a De Morgan's, and you will get the max terms. And we can do the same thing for F2 as well. So we have got M0, M1, M3, and M4. Sorry, M0, M1, M2, and M4, as you can see. So X prime, Y prime, Z prime, X prime, Y prime, Z, and X prime, Y, Z prime, and X, Y prime, Z prime. And if we take the De Morgan of that, we'll have X plus Y plus Z, X plus Y plus Z prime, and X plus Y prime plus Z, and X prime plus Y plus Z. M0, M1, M2, and M4. So these are all the canonical standard forms that we have got. And we need to understand when we want to represent the min terms and the max terms, the differences over there from the function.